for the Basic Science Core Seminar Series. So Dr. Xiong Jiang received his undergraduate training in computer science, a PhD in experimental psychology, and a postdoctoral training in computational neuroscience and brain imaging. Currently, he's an assistant professor of neuroscience and the director of the Cognitive Neuroimaging Lab at Georgetown University Medical Center. His lab has been investigating the neural mechanisms underlying neurodegenerative diseases, such as HIV-associated neurocognitive disorders, using a combination of behavioral tests, brain imaging, and computational approaches. His work has been supported by NIMDS, and other federal agencies and foundations. And with that, I will just like to Dr. Jiang to share his screen and do his presentation.
Thank you, Dr. Brodsky, for your kind introduction. So I'm going to share my screen here now. Can you guys see my screen here fine?
Yeah, perfect.
Okay. Okay, great. Yes. Yes, thank you everyone for being here, and also thank the DC-CIFRA for the opportunity to present some of our most recent work, and also, of course, thanks to DC-CIFRA, especially Alan and Maya, for all the support throughout many years. Probably more than like 9 years ago, something like that. Yeah. It's been really wonderful journey for me, and thank you guys. So today, for my talk, I'm going to mainly focus on one of our most recent publication and a pilot study to using the simulated brain stimulation to treat or to improve brain function in people with HIV disease. And this brain stimulation technique is called transcranial direct current stimulation. Basically, it's just flow for a really weak current into the brain to modulate. Of course, before I can talk about a study, I give a little bit of background here. So I'm going to first briefly talk about what's the kind of challenges we have in the neuro HIV in general, and also we're going to discuss some of our brain imaging studies of neuro HIV in our lab at Georgetown University, and then we'll talk about the study we recently published for using the TDCS applied to the cingulate cortex to improve brain function in people with HIV disease. I guess before I start, I guess everyone here is low, and the HIV prevalence in the United States, about 1.2 million people are living with HIV disease nowadays in the United States, about 38 million or 40 million globally. And unfortunately, Washington, D.C. Probably is one of the highest percentage of people, populations are affected by HIV, is about 2% in Washington, D.C. And for people older than 50, the percentage is even higher, about more than 3%. This is just a recent annual survey from DC government for their prevalence in 2020. With thanks to the medical advance and especially the antiretroviral treatment, nowadays the life expectancy of people living with HIV disease is kind of approaching the general population. So this is a large study done by Case Permit, just published 2 years ago. So they basically looking for all the patients for part of the Case Permit system. It's a large sample size. What is found here is overall individuals living with HIV disease have the life expectancy is pretty much similar to the general population. Of course, you can see there's still a few years less than the general population. But even a big difference is how many years they can live for without any comorbidities, will be community-free. Of course, many of other diseases can be affect their life quality, liver disease, kidney disease, and lung disease. But for us, of course, for our research, we focus on the central system, our brain here. It's our key focus here. And for the brain function, how HIV is affect the brain function and cause some kind of cognitive impairment is still not fully understood. But now we have much better idea. And this is a field we get more idea, better idea, but it's still to be decided to be fully explored here. Basically, it's past the blood-brain and cause some consequence here. And at behavior level, the cognitive impairment, we generally give a more like umbrella term. We call it HIV-associated neurocognitive disorders. So this is pretty much an umbrella term covers anything associated with the neurocognitive impairment in people with HIV disease and also due to HIV disease. So there's different stages. You have ANI, mild stage. You have MND, it's slightly have some interaction with daily functioning. And the most severe form of hand will be dementia or HIV-associated dementia. All this test is based on behavior observation or behavior performance. It's most time you give patients about 12 or for that number 9 to 12 neuropsychiatric tests to ask to evaluate their performance in 6 cognitive domains, then give some kind of do some calculation, normalization, and to say whether they have a different level of impairments at different cognitive domains. If, for example, motor function, executive function, learning, memory, language, and the speed of information processing here. That's some of the cognitive domains as commonly affected in people with HIV disease. In terms of prevalence, it's kind of interesting. I know many of you guys are already familiar with our chart. So basically, it's when you look at the pre and post card, while the post card had really helped people live longer and achieve pretty much normal life, but when you looking at how HIV affects the brain function, what we found is kind of really striking is the overall prevalence of hand is pretty much not much changed when you compare to pre and post card. The biggest change is coming from the most severe form of hand dementia, but the more mild forms of hand actually it's on the rise, probably due to many other factors like including aging. Right? We now have an aging population even with HIV. This kind of prevalence also confirmed by more recent meta-analysis study just published 2 years ago in AIDS. What they found is also the prevalence is about half of people affected by hand. And interestingly, they found also CD4 later has a significant impact on the hand prevalence or on the hand. So for people with cutoff with 200, also it's a number we use in clinic assessment, whether they have severe immunosuppression or not. That's kind of one of the factors. So the hand challenge here is really they have high prevalence. So even with people who are on antiretroviral therapy, have controlled viral load, and have how to say is on medication and it's a lot it's not affect during the study visit because there is some other condition might affect their performance, but even after controlling for that, the hand prevalence is still high. Unfortunately, neural mechanism underlying hand is still not fully understood yet. And as a consequence, we don't have really proven effective treatment for hand. So that's the sense we have, of course, that's a sense really getting more and more important because we have aging population. Once they get older and older, then the HIV and the aging might interact with each other, plus some other factors might increase their chance of dementia much higher than the general population. So we did find a way to treat them. To treat them for us, I can speak this one. So for our study, we use an MRI. So that will be second half of my talk today. So how we're going to use imaging to understand how HIV affect different brain structure or pathways or networks, and contribute to hand. For us, our research mainly uses MRI. So basically, we put patients on the bed, and this is the head coil. Then we scan and acquire some nice picture of the brain. And also, I just want to say, yeah, if you guys have any question, feel free to interrupt me. And if anything is unclear or anything like you want to if you raise your hand, I might be able to see you, so you can just say it. Yeah, I will try to respond. Thanks. So with the MRI, for our research, we mainly focus on the 4 types of MRI techniques. One is structure MRI. What structure MRI doing is basically looking at the atrophy in patients. So this is, of course, it's cartoon, and this is actually from the normal control. This is the brain from the patients. Who is the patient in France, and so I give some disease, and so you can see how atrophy can be detected with MRI. And also there are another technique, it's called diffusion MRI. Basically, what it means diffusion MRI is assess the fiber tracks, because within our brain we have white matter, green matter, and CSF. Right? Green matter is more like neurons to carry out the function, but they need to talk to each other. And different parts of the region, like my front region, need to talk to my occipital or my language region for me to present, to read the slides here. So that's how the fiber track is talking to each other, connecting all the parts, more like a network. It's considered as the internet there. And another technique called MRS. So MRS basically assess how HIV disease or other brain disease might affect the change of the metabolites in brain region. Like for here, for example, here I think it's in subcortical region. So you can scan, put a scan in there, and to assess the concentration of different metabolites. For most time, metabolites assessed A is one of them as a marker of neuronal function. Then for HIV, you have choline and MI. That's more like inflammation markers. Then you can also assess creatine. Creatine is most time is relatively stable, so some people has been using creatine as more like a denominator to normalize the concentration level. And you can also assess the glutamate, glutamine, and other metabolites. And also GABA is not shown here. And there's another technique, it's function MRI. For function MRI, basically using the blood oxygen level dependent signal there to assess how the brain is doing different tasks. When I speak, when I read my slides, then different parts of my brain region will be more engaged in different tasks here. So that's for function MRI. But for function MRI, mainly is just use it for basic science research. It's not being applied to clinic field yet. So that's one of our focus in my lab. We try to push function MRI. Can we develop a function MRI techniques that can be used for clinical application or for translation research? Because function MRI has many advantages. The most important one is high sensitivity to neuronal dysfunction. So that means it might have this kind of high potential to detect early disease stages. But function MRI also have its limitations because many factors can affect how the function MRI responds in the patients. For example, for a structure MRI, if it's scan patients today or tomorrow, you would expect it pretty much same. But for function MRI, it depends on whether this person have a good sleep, or did this person drink a cup of coffee, or have in good mood or bad mood. That might have some impact on how the function MRI data looks like. So one of our main focus in the lab is, can we control for all other confident facts? Then can we extract a function MRI data that will be truly as an indicator of how the neuronal function in the brain, driven by disease or aging or other factors here.
Xiong, quick question.
Sure.
The diffusion MRI, the second one, are you looking at blood vessels or neurons? What is that? What are those?
Hey, Alice, yeah, thanks. Yeah, for our research, we don't use diffusion MRI looking at stroke, like people have been using diffusion MRI for stroke patients. For our research, we've been using diffusion MRI to look at the white matter injury, so the fiber tracks. Yeah, we are like looking at stroke using diffusion MRI in this study.
So you're looking at the brain matter.
Yeah, brain matter, just a gray matter, just a white matter here. Yeah.
White matter.
Yeah, so how, because when during like including HIV, aging, and many other disease, even at very early stages, they might have some kind of impact on the microstructure of the fiber tracts of the white matter injury. It's using traditional like FLIR imaging. Because there's low lesions, you cannot detect it. But use diffusion MRI, you might be able to capture this kind of really mild change.
Hey, can you go back to the schematic about the blood-brain barrier?
Which one?
The schematic, go back. Back.
This one.
Yeah.
Yeah.
Migration of activated monocytes. Sanjay, a question for you. Is this where the platelets come in? Because I remember your talking about the platelets bringing neurons across the blood-brain barrier.
How the virus cross-blood barrier actually is, I think the popular idea is probably through the macrophage, or but there is some recent some groups they suggesting the CD4 might also play a role. So of course I'm not a molecular person, so.
But Sanjay is, and Sanjay has an R01 on this. So I just wanted to hear his.
We don't have R1 to study the blood-brain barrier. Yeah, we don't. Yeah, I think there's someone else at the CFR might have one.
Yeah, you're right, Alan. What Xiong is saying is that HIV enters in the brain through infecting cells, and the cells migrate into the brain. And that migration is kind of modulated by multiple factors. The platelet is one of those. And that's what we study. But HIV can directly cross the blood-brain barrier and get into the CNS, but the functional role of that is not described yet, because the half-life of free-floating HIV is very, very limited, or very short, and their ability of infecting cells is also very, very low. Basically, HIV transmission occurs through cell-to-cell contact. So primarily, the cells carrying HIV are the major concern for the brain.
Thank you. I just remember your talk so vividly talking about platelets right at that interface. That was pretty recent.
I'm thrilled you remember it. That was quite a long time ago.
Thank you, Jiang. Sorry to interrupt your talk.
Yeah, thank you for the really much better explanation. Yeah, as I said, I'm not really molecular or neuroscience person. So
no, but Sanjay is, and I just wanted to hear his perspective. So thank you. That's helpful.
Yeah, it's good. And also, how the HIV translate into the brain, as Sonia mentioned, there is some additional data, more recent data, suggesting there might be multiple ways there. Yeah, not just one, just through one channel. Yeah. So, any question about the different MRI techniques here? Okay. So the first one I'm going to talk about is the structure MRI. So as you can see here, this is a type. This might be no, it's not my brain. Maybe it is, I forgot. So it's a typical adult's brain here. You can see a nice T1 weight image here with green matter and white matter, and ventricles here, and brainstem here, and the cerebellum, cortical region. And so with structure MRI, most time people looking at it, how disease, including HIV disease or aging, or development disorders is going to affect the brain structure, where they have get increase in volume or decrease in volume, or the ventricles might get expanded, right? For aging, for HIV or Alzheimer's disease. But the literature on this one is deeply inconsistent. So a few years ago, with a work from a master's student in the lab, Sarah, so we did a really comprehensive literature review. So we basically go through went through all the publications in HIV and structure MI, and we want to see what's kind of most common finding here. The key question we want to ask is, when we compare patients versus control, which region is more likely to be affected? Then within patients' population, if we compare patients with or without hand, or with or without cognitive impairment, right? Then which region is more likely affected? Because then this will tell us what some potential mechanisms or some potential target for treatment. So we did using a technique developed by two colleagues at Georgetown University, like Uma and Peter Togado. So we did a study. The idea here is for each study, we just assign where they find the change in volume, either at the global level, like front lobe, to define whether HIV disease is going to have impact on the front lobe, or versus parietal, or versus temporal lobe, or versus cerebellum, which will know whether more likely affected, or limbic system, or subcortical region. Then we can say within, for example, if we say, okay, they found the patients versus control, they more likely have a subcortical injury, then we can focus on within subcortical injury, within subcortical region, is more likely being the caudate, or pituitary, or thalamus, will be more likely affected in patients' population, or how this different injury in different regions might contribute to hand. So that's our main question here. So what we found here is interesting. I'm going to skip this figure because it's a little bit too busy here. Let's focus on this one. So here, basically, idea the first contrast we did is for patients, for control versus patients here. What we found is across all studies, across all the literature, it seems to be frontal regions, the region is more likely to be affected in patients' population. And within the frontal and also plus subcortical region, if you look at it, just individual subregion here, then the cingulate cortex, especially the anterior cingulate cortex, seems to be the most consistently affected region in patients' population. But how about within patients' population? We look at patients with who are cognitively normal without hand, or cognitively impaired with hand, then at this level, at the more global level, it's need to be unclear. But when you look at the individual region, how they contribute to hand, looks like the stratum, especially the caudate, seems to play a major role there. So this has some kind of really interesting implications, because we know before the antiretroviral therapies are available, like before CAR-T, like in 1990s or early 2000, then most profile of injury is basically associated with subcortical region. Back then, if a person without hand or without CAR-T on treatment, by large, the injury is more likely focused on their behavior impairment is associated with basic ganglia and subcortical region. But since the CAR-T is become available, there are some like ideas suggesting whether this can be the profile of the injury is more likely associated with frontal region. Subcortical region is no longer as important as a previous as pre-CAR-T area. So here, at least based on what we with all structure, of course, limitation here is we only look at the structure MRI here, suggesting yes, frontal injury probably is most prevalent in patients' population, including the ACC region. But when they are at more advanced stage of disease, subcortical region might still play a more important role here. So based on this data and based on animal study across the board, so we come up with very simplified neural model of hand. First, I want to please. All right. So this is a neural model of hand we proposed. This is really very, I want to make it clear, it's very simplified. It's very likely have some, there's some of assumptions for this model is likely not being inaccurate. we might need to be revised. And also this one of this model didn't including regions like cerebellum, because we know cerebellum also is one of the probably sites has been commonly observed injury in patients population. But nevertheless, we think nowadays we have to think a different way to define or to characterize hand, because if we only rely on the golden standard behavior testing, we cannot really identify potential neural targets for treatment, because it's based on behavior. Then one person diagnosed with hand might be very different from another person diagnosed with hand. Maybe this person have motor response, this person might be a learning memory, and this person motor response might be due to basal ganglia or due to cerebellum. This person's learning might be due to frontal or basal ganglia region. So how can we be able to identify? As we with the more like MRI image, especially MRI brain imaging techniques now widely available, we should think about how we can be able to revise the hand model to including findings or data from brain imaging and also from animal studies together, not just rely on behavior observation. So in this way, we will be able to better identify potential targeted treatment, and then might improve our chance to find a more effective treatment for hand. Just for next direction here. So basically, in this model, we just make an assumption, make this prediction is for people who have really mild forms of hand or pre-hand stages, they don't meet the cutoff score for hand. The injury is more likely driven by frontal injury. So, in that case, you can as we know, in the people with in the patients on antiretroviral treatment, the most likely observed cognitive function being disrupted or being impaired in patients population is executive function is one of them. It's really associated with a frontal cortex here, including speed of processing and other things there. And also we propose once for people who have a hand probably very similar to the pre-cut area, then this kind of more severe forms of cognitive impairment might be still driven by subcortical injury, especially the caudate and the stratum in general. So that's our prediction and the hypothesis there. And to summarize, basically, we think frontal ACC injury is highly prevalent in patient population, but in terms of cognitive impairment, probably is better predicted by subcortical region, especially stratum and caudate. So now of course, this is more like a review paper, and also it's more of a meta-analysis paper to give this kind of general framework. So we want to understand how this can be linked to our own patient population. So this is what we try to identify how medical history will contribute to a brain injury in patient population, how other comorbidities like depression, substance abuse, hypertension, liver disease, and also other disease, how this, including alcohol abuse disorder, how this can contribute to hand or cognitive impairment in general. And also we think about below genetic risk might play a factor, especially it's important because we have aging population who are living with HIV disease. Then we know some of the genes have a risk for cognitive impairment. Okay, one of the most known one is APOE4, because APOE4 has been the strongest genetic risk for a late onset sporadic AD. So how APOE4 might play a role to affect the brain function in HIV population, especially people for aging population there. It's also an interesting question there I want to study. So first thing we did studies for control group patients to use structure MRI, and this work is done by lab technician Craig, and also with postdoc Kyle, who is now a faculty member at Georgetown University. And so we did a comparison. We have 100 patients and 44 controls. we use different types of techniques, imaging technique to looking at the difference between patients' controls. And then we, of course, we we correct for multiple comparison here using standard guideline and threshold in the literature. So what we found is there is a difference in the front region. It's in the apical front region. There is a reduced volume in patient's population. But we didn't find the significant results in other region. There is some like there's some also dramatic reduction in some other region, but they don't survive the correction for multiple comparison, including the ACC and dorsal prefrontal region. So just in terms of this finding, is we found that there is some difference in frontal region, but in general, the effect seems to be relatively small and it's not super strong. And then we try to understand how HIV disease severity and like medical factors might contribute to brain injury. So here we're looking at CD4 leaders. Of course, CD4 leaders is the lowest ever CD4 counts. So this people have been using CD4 leaders as a measurement for the depth of immunosuppression in the past. So it has been generally have been recognized as a legacy effect. So if a person have really low CD4 leader, even like 20 or 30 years ago, they might still have long-lasting effects on the brain structure and function nowadays after 20 or 30 years. So that's why we try to study, and because of CD4 leader also has a strong predictable cognitive impairment. So here I'm going to skip this one because we are needing tight on time. Yeah. Also, this study by grad student Shiva and our previous postdoc colleague at Georgetown, Kyle. So here we're looking at the cortex thickness here. Basically, this is the structure. Right? This is our PR surface of brain tissue. Then this is the white matter green matter boundary here. And basically, for cortex thickness, you just examine the distance between the two surfaces. So this has been a really standard technique and also be highly sensitive to disease and to aging, including aging and development. So here we use this to assessment. What I found is low CD4 leader is associated with widespread cortical thinning, especially in the frontal and in the temporal region. Suggesting that a severe immunosuppression back many years ago might still contribute to the brain injury nowadays, 20 or 30 years later, and including some brain structure change, and also looks at the frontal region and temporal region by the injury to the frontal and the temporal region might still persist after 20 years. Also 2 years, long time. So in addition, we also check out how the cortex thickness associated with brain function, associated with cognitive function in general. So here we use GDS score. It's very interesting. The findings mainly in the frontal region, and also what's even more interesting is even in patients without a hand, so they are still cognitive normal. The cortex thickness in the frontal region actually still correlated with their cognitive function. This is after correction for age, education, and other demographic factors, suggesting that frontal injury is really plays an important role during this kind of early stage or more mild stages of the hand. This one, of course, there is some cavities. Once later on, we increase sample size, including additional subjects, the effects can be washed out. We still kind of the difference in the ACC and the temporal region and some frontal region is still there, but it's much less significant than we highly expected. Depression is another. It's highly prevalent in patient population, so it's about 2 or 3 times prevalent. And with low depression in patients, even with HIV disease, has really a adverse effect. So patients with depression is more likely to have kind of worse outcome, including cognitive impairment, viral suppression, and also higher mortality rate. But how depression is going to affect the brain structure and function in HIV population. Actually, it's, to my surprise, it's it's really understudied. And so far, we have done quite a few search in the literature. We only come across really handful study to study depression in HIV population using brain imaging. So here we want to just do a study. So with the instructor mice study by a lab technician and also a previous master student, and together with 2 postdocs. We classify patients with two categories, with or without depression, without depressive symptoms. We assisted with the BDI score. What we found is individuals with depression tends to have a smaller hippocampal volume bilaterally, and they also in the left hemisphere also have a smaller occipitofrontal volume here. But here we only right side survive, only right side survive the correction for multiple comparison. And this is interesting because in literature, in general population, also depression has been associated with a smaller hippocampal volume across many studies. So we skip this one. And this is, we also examine how HIV disease itself is going to interact with depression in affected brain structure. What we found is interesting here. We didn't find any interactive effects. What we found is more like additive effects. So looks at the HIV disease severity. Here we disease severity is captured by later CD4 count. HIV disease severity and depression seems to be more like independently affected brain structure. So more like additive effects. This is interesting, has its own like a interesting implication. We are trying to study in R21 we just submitted. So can we link the brain imaging with molecular and similar blood markers here to study what kind of mechanisms might contribute to this kind of additive effects here.
So excuse me. So here the CD4 is the whole blood, right?
Yeah.
Can you add the CD4 in CSF?
Oh, I'm sorry. This is CD4 later. So this is large carrying CD4.
Okay, thank you.
Yeah. Good point. Yeah. Thanks. I'm going to, since around time, I'm going to skip the study with AP4. Basically, AP4 is here. What we found is, when we come to the conclusion, is we find actually HIV disease severity seems to be exaggerate the impact of AP4 in adults with HIV. So the implication is if a patient has a history of immunosuppression, that means they have a low CD4 later, then is the AP4 carries. These individuals might be at a much higher risk of the development of some kind of colon impairment later in life. So this is kind of suggesting we need to for the field we will need to think about it, because we have aging population. We have to think about how the genetic risk and age might interact, and plus disease. Now we have three-way interaction. How this going to put some of our patient population might be so vulnerable. We need to find a way to help them.
So, Xiong, one quick question, and I believe that these are not obese patients, but with the ApoE alterations, you can expect the atherosclerotic events also in these patients, right? So, is there any indication that whether severe form of cognitive impairment in the brain is linked with atherosclerosis?
I'm not familiar with this field. Yeah, there is as I was saying, I think this is more like a understudied field, at least based on my the literature I come across. Yeah.
Okay, thank you.
Yeah, sure.
Jiang, I have also a question following Sanjay's question. I was wondering if you look to systemic inflammatory markers in these individuals, because you have low CD4 counts, it's very likely that they will have high levels of immune activation.
Mhm.
Did you look to systemic markers to see correlations like CRP or the typical D-dimers that will be also upregulated in arteriosclerosis, actually?
Yes, that's actually in our in the grant proposal we just submitted back
Okay.
last week. Yeah. That's a good question. Yeah. So it's definitely it's one thing that we try we want to study and we of course my lab is not really have the expertise in like molecular or blood markers, including CRP and IL-6. Yeah, and also we including a few other markers that we also try to study as well, because it's one of the things. It's I think in the end we want to understand, right, how the system together, as Sonia said, affect the brain function, how they contribute to how we can be a link at the macro level using our brain imaging technique to the micro level at the in the blood. Even better, it would be CSF, but we try not to collect in CSF from our patients because if our study is not a clinical trial study, we did lots to help them. I just don't want us to contribute too much with CSF there, so we just collect blood. But you with peripheral markers, I think it can still be pretty indicative what might happen in the brain, but of course it's not always 100% there.
So I maybe missed it also. What age is the cohort of
the cohort is the median age is 56. Yeah, it's in the age range of 41 to 70. So it's like middle age, the transition period from middle age to early age. That's our intentionally we try to understand, because with aging population, we try to say when they move to the geriatric age range, 60 and above, how the aging might play with role with the HIV to affect brain function. So we were, of course, our goal will be follow up with longitudinally. So that's our current study is going on. We try to ask them come back and scan them again and to see how their brain and structure and function is changing from. We try to scan them every 2 years.
Okay.
So we'll be very interested to once we have the data.
Thank you.
Sure, thank you, Matt.
I wanted to comment on what Dr. Magdevor said. So this about the cholesterol thing. So both CH25 and CH25H plays a very important role, and they are kind of, especially CH25H is kind of a restriction factor. And I have also worked it out, and we are about to publish in sickle cell disease. So
that's great.
So that's what I wanted to comment, that it could be that cholesterol, atherosclerosis and all that may be involved in.
Yes. Okay. Yeah. If possible, if your answer paper is accepted publication, I would love to read your paper. Yeah.
Okay.
So now I think I need to read. I need to move to just think about it. So now we studied this disease with different module here, and the goal is for us, of course, the goal is really to help the patient population. So, but we have once in a week. I think did I have it here? Not here. One really thing that really bothers me a lot. Also strikes me a lot is unlike when we used to study basic science, to study our most subject previously is mainly college students, right? They are really homogeneous here. But when I get into the HIV field, what I really found is really very, very striking and very, very exciting is each patient is more like a case study. They're so different. So that's, of course, it's going to affect how well we can get the same results. But at the same time, I think it's really exciting because this really opens up the door for many, many exciting questions here. So how are we going to be able to assess treatment at the individual case to help them to develop some kind of technique to treat them? And how we'll be able to find some common mechanism associated with just with disease and also might play a role here. So that's and in that case, how we're going to under this principle, they might be each individual might be a different case. At the same time, they might share some kind of income a pathway in terms of brain function. How we can link this together to develop some treatment for them. So our TTCS study is one of them. So we try to come up. Here is as our model, right? I just it's really frontal ACC injury. It's really highly prevalent in almost happens is precisely in everyone with HIV disease. Suggesting like frontal ACC might be a potential target for treatment, right, to improve the function. But the frontal region, of course, is just so large, right? If we don't know which part of the frontal region might contribute to frontal injury. So in this study, we focus on ACC because it's relatively a small region area we can focus on to study. So this is our why we developed this study. So we focus on ACC. This is the anterior cingulate cortex here, mainly because we find that ACC is really highly prevalent injury. Injury to ICC is highly prevalent in people with HIV disease. And also because we found in another study with 2 undergrad students, we found is in the cat area, the injury, the contributing factors to hand seems to be one of the markers NAA. NAA, of course, is a neuronal marker, right? It's only look at the process inclusive in neuron the process here, suggesting NAA reduction might be a marker for neural dysfunction. They were suggesting in addition to neural inflammation control, if we can improve neural function, might be able to help to them to improve their function. But of course, which brain region we should target? Then we choose ACC because we think ACC is one of the most commonly affected region. Even we have really highly diverse population, but for many of them, ACC might be a region has been affected. So that's why I focus on ACC in this treatment study. We use a neuromodulation, especially we use the TDCS because it's safe and can be well tolerated. And TDCS is really a non-invasive brain stimulation technique. It's not directly excite or inhibit the neurons. Rather, you can just change the resting membrane potentials to make them more likely or less likely to fire. Over the past 20 years, there have been many studies has been trying to use the TDCS to treat different psychiatric or neurological conditions. And even at this stage, we still don't fully understand how TDCS works. We have a bad idea. It might be shuffling of the change the excitatory inhibitory balance there. But for the underlying neural mechanism, we don't fully understand it yet. So unfortunately, HIV, very few studies have used the TCS to treat patients. Based on the literature we searched like late last year, only 6 published studies. In addition to ours, only 6 published studies to use this kind of non-invasive technique. Non-invasive brain stimulation technique to treat HIV, including another study 10 years ago to say how with open label design, TDCS can improve the mood in patients with population. There's 5 single blind design. So patients are not aware of treatment, but the technicians are aware of treatment assignments. The 5 study use either left dorsal prefrontal or right dorsal prefrontal as the target region to see whether TCS can help there. The study from this 5 study, the results from this 5 studies is kind of mixed, but there's some positive findings here. So here we think, for our point of view, based on what we have been reviewing in literature, we think the ACC might be a better neural target for treatment because its injury is really highly prevalent. Because then when you target the front region, each person might have different parts of front region might be injured. So that means for some patients it might not be so effective, and that might affect the study outcome.
So Xiong, one quick question. How durable the effects are of this stimulation? So like after 10 sessions, how soon the behavioral studies were done?
Behavior. So in general, I'm going to go to that with our experiment design. I'm going to touch that part.
Okay, okay.
Okay, good. Yeah. So this is a collaborative study with Peter Takab and also with Prince Kuma in here. So Peter Takab is really expert in brain stimulation. So this is studied by a lot. Even it's really this is really small pilot study because it's takes up a lot of human resource and because each patient come in 10 sessions, coming into our lab 10 days. Then they did have assessment before treatment, after treatment, and then the follow-up study. So this is really large efforts, and so you guys can look Princey, she's a part of study. So we only before the pandemic, we only be able to finish the study with 11 subjects. And since the pandemic, we our funding is also for this pilot study is finished. So we didn't get any chance to add any study here. And we assigned as baseline, we assigned to 2 groups. One group received real TTCS, another one received the sham. There will be double blind, so both the technicians and the patients don't know their assignment here. And let's get the detailed technique here. So because we try to stimulate the ACC region, right? So based on simulation results, so we come up with this assignment. So we have 2 anodal positive electrodes. If this will be anterior frontal central line, this will be central part region, also central line. Then we have 2 temporal T7, T8 electrodes for inhibitory there. And based on simulation, we it's the simulation the excitation in the ACC, those ACC is pretty good. So we use this setup. We did a study, and each patient will have 20 minutes for active or sham TTCS. Then the patients also will be reporting their discomfort ratings using this. They basically tell us how discomfortable they might feel at the end of the electrodes. So this will be assess the safety and the tolerability here. They will also assess the different types of the function. And we also, after each session, we also give them a cognitive training with different types of cognitive training because we want to be able to generalize the treatment effects. So they give them different types of cognitive training. So go back to the question about how we assign the treatment effect. So baseline, we have baseline visit. At baseline visit, they will have an MRI scan. Then we'll also go through the neuropsychiatric battery to assess how what's their cognitive performance here. Then there will be assigned to one of the 2 groups with the randomization here. This will be this phase 1 will be double-blinded. Then after 10 sessions of treatment, then we'll have 3 follow-up study visits to assess how well is their cognitive performance looks like, and what's their brain function and the brain structure looks like using MRI at each of the 3 follow-up visits. Does this answer your question? Sorry, I didn't say name there.
Yes, yes. And you know what? Another thing I was thinking about is that so far in the field, the neuronal injury was kind of implicated in the behavioral changes, but no one has definitively showed that, because there's no way we have any kind of intervention. So with this kind of technique, you can really link the protection versus protection with the behavioral changes. They'll definitively link it.
Yeah, that's our hope there. Yeah, it's also our one of our hypotheses there to drive this study. Thanks, yeah. So then after the phase 1, we will unblinded the experiment design. Then the patients who receive sham, they will be given the opportunity, if they want, they can come back for the open label real treatment. So then we finish study, and skip this one. We collecting, as I said, we collect data from neuropsychiatric battery and the MRI scan here. And for data analysis, we focus on the 3 cognitive testing that have been associated with frontal and ACC, especially have the like Wisconsin catastrophic game sorting test, has a really direct link to what is one of the most commonly used instrument to assess executive function. It's called word test and the trail making test. Let's skip this one. So in the Wisconsin catastrophic test, there are different, of course, different measurements here. Most commonly used one is two types of errors. One is called non-preservative errors. That means they just randomly make mistake. Another one is preservative errors. This one is very interesting because this one has been basically this one means if they make a mistake, then they're being told that you have made a mistake, but they just refuse to change. They will just make the same mistake again. Compared to the first one is random error, right? You have to try and find out the rules here. So you make a random errors here. So this is the load is there. The load the rule that you just use is not right. They will still just stay with the same rule again. So let's say this type of error has been associated with structural injury to dorsal ACC and prefrontal cortex as well, especially right prefrontal cortex. So that will be since the ACC is the region we are targeting, we think that would be like a good exam or good test score to look at. First thing is pain scale. We don't find really good any difference between patients receive the sham or receive real treatment, suggesting this really singlet disease can be real, is safe and also can be well tolerated because the patient couldn't feel the difference here between the two. And the most exciting finding for this study, actually, one of the most exciting study here is we found that after the patients receive the real treatment, they made less errors in the preservative errors. Basically, they suggesting they are being more flexible to change the rules if they know they made a mistake. And also, what's really exciting for us is, I think every single patient, even have a small sample size, every single patient who receive retreatment, they show a reduction in the errors, not just a group effect. It's just every single subject, they also showing the effects here. And also the effects can be last for a while. Compared to patients receive sham, they don't have much difference here. Once we switch the patients to real treatment, they show there's some encouraging signs, suggesting I also show some improvement here as well. This is in contrast to the non-preservative error because this is random error is a lot associated with ACC. So we didn't see much difference here. Another change is we didn't also see much with soup task. Another thing we say is with the trail-making test. This is the measurement has been linked to cognitive flexibility, including ACC. Also, we say improvement here as well. Let's skip this one. We also look at brain imaging data. We don't see at structure level, we don't see change in brain matter volume or quick sickness. But when using the resistant connectivity, we use the ACC as a city region. We find that after treatment, there is the increased connectivity between the ACC and the dorsal stratum here. This is just extracted the connectivity between the two clusters and showing the connectivity here. You can see from baseline there is a change. Of course, there is washout effects there. Washout. This is after 3 months. This is after, I'm sorry, I forgot to say. Baseline is right before treatment. Follow-up. The first follow-up is about 1 week after treatment. This will be about 3 weeks. This will be about 3 months after. And also, interestingly, there seems to be a correlation between the change happens with connectivity and also the change in behavioral performance there, suggesting the change might contribute to their improvement in cognitive function. Just a quick summary. So TCS is safe and seems to be able to help patients with help to improve cognitive function patient population, especially for the cognitive flexibility. And then, of course, we need to verify our findings in a future study. That's one thing we have been working on. We want, hopefully, we can get some money from NIH to make it much larger study and also with full crossover, because this is partial crossover. Only patients who receive sham will be invited back. So in future, we want to do full crossover study. This one. Just want to thank all the our subjects. Really, without them, we cannot do anything. And my lab members and collaborators and this is Safer XP Island and Maya. You guys have been really tremendous help for my researching during HIV from very beginning, like many years ago. Thank you guys. And our study is really funded by NIMH and NBS, and also some including and also CIFRA and the other Georgetown and other foundations. And this also our facility, our CRU, our the clinic infectious disease unit under the lead of Dr. Kuma, and she really be help us to recruit subjects and provide some clinic suggestion, and our clinical research unit for help us to study the carrier study on the MRI center and our department here. Thank you guys. Sorry, it's been still too many slides. Questions? I know I run out of time, but if you guys have any question, feel free to email me. Yeah.
Okay, well, thank you so much. It was an impressive talk. Is there any questions? Is there any mentee, any graduate student, postdoc that has any burning question? That wants to? I do have a question, but I want to wait to see if anybody else has a question. But my question is, and I'm not as familiar with neurocognitive disease. So my question maybe is already known or it may not be, but has anybody looked at whether because even in the presence of ART, 50% of people living with HIV will end up with some type of neurocognitive disorder. So is there, and you've been looking at the correlation with CD4 nadir, that is just, the lowest number of CD4 T cells. But has anybody looked, and it may have been done, whether there is any correlation between the development of a neurocognitive disease and the size of the latent reservoir? That's I'm asking because obviously working on HIV cure and reservoir, because I'm thinking that in people living with HIV that are taking antiretroviral therapy, the development of that neurocognitive disease is probably associated with still the presence of HIV and the reservoirs. I may be wrong, and Sanjay, you can correct me if I'm wrong. But is there any study like that has been looked at into? Sorry, that's
that's an excellent question here. Yeah, so there are some study looking at it, but in general, like of course with post-mortem study and looking at how the viral load in the different brain tissue or might be associated with their coding impairment at hand before they passed away. There are some interesting about it to a large degree. There seems to be more robust correlation between viral load and the coding impairment before CART. But after CART is available, the association between coding impairment and the viral load seems to be really much, it's kind of really diminished to a large degree. So, for example, if we look at the viral load, people with undetectable viral load or people with detectable viral load, then there's no clear association with the coding impairment. But if you actually, even when including carrier CD4, for some study, some probability might find effects, but it seems to be more like CD4 laters seems to have been more strong impact on brain function.
So let me add in it, Alberto. So it is common consensus so far is that the disease progression is not associated with viral load more than it is associated with the immune cell activation in the brain.
Okay.
But that observation, that study, I think it is overrated. And it's a time for reinvestigating the viral reservoirs in the brain, because more and more we learn about it. The reactivation is linked with the inflammation, and it's bound to have effect on the brain. So,
yeah.
So that's the possibility, but it's not tested yet. So we need to revisit that study.
No, I
Yes,
mean,
yeah. Go ahead.
No, I was just gonna, I mean, obviously working on reservoir and thinking about, that in that case is not associated with the viremia, is going to be more associated with the time that the participant is being without antiretroviral therapy, that at least in CD4 cells, sorry, is bigger, the reservoir. And then in some cases, in some participants where you see it is that reservoir is more inducible than others, so there may be more proteins produced. So, I wonder if that that is leading to more inflammation, that it may be leading. So it was, if there was any study like that, because that would be interesting. And obviously then you have the reservoir in the brain, which is going to also be really important, obviously, for hand. So yeah. I mean, I'm not, I don't have any knowledge on the brain reservoir. That's not, but yeah.
Yeah, that's good to know, because I have limited knowledge about the different types of reservoir, and it's, as I said, I'm a basic neuroscience person. But there is some study published a few years ago. They're looking at like brain tissue with looking at viral using RNA and DNA and the comparison. I don't remember the exact finding there, but that study suggesting the viral replication or antiviral blood in the brain might still contribute to inflammation and to some level of the current impairment, but by large, the value itself seems not really have a strong impact nowadays. And for, as you mentioned, for reasons we don't fully understand yet. They might be due to the different types of river there. It might be due to some other host gene and the host factors that might all play a role there. So we don't fully understand yet.
Okay, well, I think we are like 10 minutes over the time, but if anybody else has any other question, I think they can email directly Dr. Jiang. We really appreciate your taking your time to present to the basic science core for the DC-CFAR. I'm hoping that it seems that some people are starting to get some ideas on potentially how to collaborate among different institutions. And if we just, I'll enjoy your weekend.
Okay, thank you guys. Yeah.
Great talk, Xiong. Thank you.
Yeah, thank you guys.
Thank you.
Email me any question there. Yeah.
Sure. Bye.
Bye.